All right, today what we're looking at is Euler's number E, and we're going to explore the constant E, understand where it comes from, and apply it in exponential models. So the gradient derivative function, which we haven't talked about derivatives yet, but we did do it in our taster lesson last year. So the gradient of a function is also called the derivative. So the gradient is where we have little tiny gradients going up the curve. Okay, the gradient function of an exponential function is always increasing and increases at an increasing rate. That's the same as an exponential function. An exponential function is always increasing at an exponential rate, okay, unless we manipulate it to be decreasing, where we saw that last lesson and we flipped the function about the y-axis. We have, if we can sketch the derivative function of an exponential function in blue, then it is to an exponential function. Okay, we don't need to know too much about that. It's just showing us what's happening here. And so below what we have is the graphs of the derivative functions in blue of y equals 2 to the power of x and y equals 3 to the power of x in red. Okay, we will look at the derivative of exponential functions when we touch differentiation later next term. Right, for now, you just need to know that that's what they look like, okay, that it's the same as it is. What we can do is we can notice that the graph of the derivative function is a constant multiple of itself. So we have for our first one, y equals 2 to the power of x, it is y equals 2 to the power of x, but it's just been multiplied by 0.6931. And then for our y equals 3 to the power of x, it's just been multiplied by 1.0986. Okay, so that the derivative of y equals a to the x is y equals k a to the x. We can also notice that the graph of the derivative of y equals 3 to the power of x is very close to the graph of y equals 3 to the power of x, so you can't really see the difference between that blue and that red line. That means that the value of k is close to 1, so we're only really multiplying by 1. We can find a number close to 3 that gives the same derivative function as the original graph. This number is approximately 2.71828, and it's called Euler's number E, so like we saw in that video. So the gradient derivative function of y equals e to the x is the same as the original graph, where e is approximately 2.71828182845, continuing on. Okay, and it's called Euler's number. It's a transcendental number, irrational number that cannot be expressed as absurd. What we're going to do is we're going to look at how we can graph the exponential function y equals e to the x to start off with. So what we're going to do is we're going to need to know where e is on our calculator. Okay, so on our calculator, if we turn it on, what we have is E is the number 8. So shift 8 gets us E. So on our calc, we do shift 8. So remember, anything in blue, we press shift to get to it. We then need to press our square, like that button, our power button, I suppose we could call that. I'll just circle the buttons that you have to press, and that then creates our power, okay? So what we're going to do is we're going to draw up a really basic table of values. So we'll have our x values, our y values. The first value that we might substitute in is -2. So we sub -2 in. We're going to get this as a decimal. We're just going to do it to 2 decimal places. So 0.14 when we substitute in x equals -2 into our function y equals e to the power of x. Okay, then what we get is when we substitute in -1, we get 0.37 to 2 decimal places. When we substitute in 0, we get 1, because remember, anything to the power of 0 is just equal to 1. Okay, so no matter what the base is, it's always going to equal to 1. When we substitute in x equals 1, we get our 2.72, so that's our Euler's number, E. So that one there is just E. Okay, and then when we substitute in 2, we get 7.39. That's probably enough. We'll be able to see the general shape. Okay, so an exponential function looks exactly like what we were sketching yesterday. not yesterday, the last lesson. So we're going to have our y-intercept is at 1. Okay, we also are going to have an asymptote at y equals 0. So that means it doesn't go below our x-axis. So you can draw that on if you'd like so that you know that it doesn't go, but you don't have to draw it on every question. Now, when we're at 1, we're going to be at 2.7. And when we're at 2, we're going to be at 7, which I think 7 goes off the graph. So pretty much what we want to do is, with our exponential functions, they don't need to be exact. That's why I've given you grids that don't have axes on them, like numbers on them, because all we want to do is put where number 1 is, we're going to put our point 1, and we're going to call our y value e there, okay, because that is where e is, and then we need our y-intercept of 1 on our graph as well. Trying to draw a nice smooth curve and writing that this is y equals e to the power of x. So it looks exactly like the exponential functions that we were sketching on Wednesday. Okay, it's just that we have the base of e instead of our base of a number, which was 2, 3, etc. All right. Once you've done that, flip the page and we're going to have a little look at our applications question using E. So our applications question using E is a salmon population. So the salmon population in a river over time can be described by the exponential function P equals 200e to the power of 0.3 t. Okay, where t is the time in years. So when we're looking at exponential functions, you might have heard of exponential growth and exponential decay. So when we're doing an applications question, that's what we're talking about, our growth and our decay. Now, in this case, because our power is positive, so it's positive 0.3, it means that we're going to be growing our population. If it was negative 0.3, it means it'd be decaying our population and our population would be going down. So what we want to do is we want to find the population after 3 years. So the first thing that we're going to do is write out our equation P equals 200e to the 0.3 t, and then we're going to let t equal 3. So what we will have is P equals 200 e to the 0.3 lots of 3, and so we then just put that into our calculator. So we'll go 200, shift 8, our power button, 0.3 lots of 3, and when we do that we get that P is 491.92062 ... Okay, so our population, now we can't have parts of a salmon. All right, in a salmon farm, in a river, we're not going to have parts of a salmon. So what we have to do is we have to round to 492. Okay, and because we've rounded up, we need to do our little approximate equal sign. So that's our little squiggly line that means approximate to. Okay, we then, because it's a worded question, we want to write a worded answer. So the population of salmon after 3 years is 492. Okay. Now, for part B, so we've worked out the population of salmon after 3 years. Part B now wants us to draw the graph of the population. Okay, we can't have negative time. Okay, so t is in terms of time, so we can't have negative time, so we're not going to have it on the left side of our y-axis. So we're only going to be dealing with the right side of our y-axis. So we have our equation P equals 200e to the 0.3 t. Now, how we sketch this is we just do a table of values, or we do it on our calculator. We don't have to write it down. I like to write when t equals 0, P equals, and then work it out on my calculator and just write it down instead of drawing up a table, so it's a different option. So when we substitute in t equals 0, we get 200e to the power of 0.3 times 0. So 0.3 times 0 is 0. E to the power of 0 is 1. 200 times 1 is 200. Okay? So when we substitute in 0, it's always going to be the number out the front. Does that make sense? Okay. When we substitute in 1, what we get is P equals 270. That's just rounding to the nearest. When T equals 2, we get P equals 364. When T equals 3, we get P equals 492. And we already worked that out in part A. So this one here was our part A answer. So we didn't even have to recalculate that. T equals 4. We get P equals 664. And when T equals 5, we get P equals 896. So when it comes to you sketching one of these yourself, sometimes they might give you the domain, so to sketch between T is 0 to 5, okay? So that means you want to sketch between it. What I would do is I would find out what your smallest value is. So our smallest value is when T equals 0, P equals 200. Our largest value is when T equals 5, P equals 896, to help me work out what my scale should be on my y-axis, which is this going to be our p-axis, and this is going to be our t-axis. Okay, so what we are going to do is we're going to go up every second square. I don't know if the square is printed nicely for you guys. And we are going to go up to the highest point will be 1,000. Then every second square, we're going to go 1, 2, 3, 4, 5, 6. Okay, we start off at when T equals 0, P equals 200, so that's our y-intercept, and then we can just plot from there. What you can also do is just do your start and your finish and draw a nice smooth curve between them if you would like. Okay, because it's not going to be exact. Oh, I stuffed it up just at the end. All right, it's not going to be an exact curve, but we want to show the general shape of it as well. That's not great. Just going to tidy that up. 5 is at 900. Oops. I'm having a bad pen day apparently. All right, like so. And that's it.